To kick off our day today, I'm really excited to welcome back to DSS Moody. Hadi. Moody is a group manager of new product development at S&P Global within market intelligence, and he leads a team focusing on applying modeling techniques such as machine learning and data science to distill information value for risk management based signals. And today he's here to discuss how NLP is a contemporary topic and in a variety of different fields. And he will also provide a framework of assessing different machine learning applications, generally and specifically on sentiment analysis. So be sure to drop your questions to Moody in the live discussion area at the bottom of the page. And over to you, Moody.
Hey, my name is Moody Hadi. I'm a group manager of new product development at S&P Global Market Intelligence. Today's topic is applications of natural language processing for financial engineering. Um, Natural language processing and supervised machine learning are really big contemporary topics in many fields. In this talk, what we'll do is we'll go through a framework for assessing different machine learning applications generally, and specifically delve into sentiment analysis. Then we'll go over two real-world NLP applications that we have in market intelligence for financial and risk management. One that leverages deep learning, and the other one leverages online learning. And then we'll cover through this talk the design, architecture, and some future extensions around it. Um, So real quick, we'll go. I'll give a brief overview of S&P Global, then we'll go through the framework of how to assess different machine learning techniques, specifically in supervised learning. There's a little shiny app in here that folks can access to play around with bias and variance trade-offs. Then we'll get into sentiment analysis. You show basically an overview of a generalized pipeline for sentiment analysis, and then go through a very quick, basically, trade-off and considerations of different NLP techniques. Then we'll go over two case studies, one on sentiment analysis for actually Chinese announcements, and the other on basically financial assignments or spreading of financial statements interactively, and then conclude. So S&P Global has really four major business lines: the rating agency, which rates basically typically large enterprises for their creditworthiness using the ratings methodology. S&P indices, which basically runs the S&P 500, the Dow Jones, and other basically indices. Market Intelligence, which is a data analytics provider focused on providing financial data and financial risk assessment for companies, small and large. Platts, which is an energy-focused arm of S&P that does a lot of research in the energy markets and does applications and analysis around those areas. So I'm part of S&P Global Market Intelligence, which focuses on basically providing different types of solutions for risk management applications, including credit risk, market risk, and operational risk. So let's go through as we've basically over the last few years, as we've used more and more machine learning techniques, this a lot of ways to actually consider how to assess different techniques for different business problems came up, and I'll highlight a few areas that we constantly basically think through as we pick basically different techniques for different applications. So to take a step back, as a data scientist, you're asked to basically solve a particular problem. Your client typically would be a business user or an external customer. They're not technical. They kind of leave it up to you to how to figure out how to solve it. So that's up to your discretion. Machine learning has a huge body of different techniques that you can use. So it's very important to take into consideration what the context of your target solution would look like. And then only apply the technique that gets you there with the least amount of supervision and basically control, so that you're not basically on the hook for a lot of technical debt and recalibration and retraining. So there's no real prescriptive method. It's really purely tied to the business problem that you're solving and assessing the trade-offs of the different techniques given the context. Um, so this is generally like our basically, sort of waterfall process for basically building machine learning applications, right? You start with data preparation, a lot of basically initial pre-processing, cleansing of data for neural networks or supervised learning, annotation and labeling of text. Now, this piece, the first piece, is really what takes the most amount of time. The second piece, model definition, is where you interact with your client and try to figure out what are the target variables and features that could be helpful. And you obviously in this area, you're going to try different techniques to figure out of this data set that you have with thousands and thousands of features, which ones are more relevant to actually hit that target. Uh, and here you might try basically lasso, random forest, neural networks, different iterative basically techniques until you kind of have an idea of which are your target features that you want the model to use. Then comes basically training and testing. Um, this is also an important piece, and really where you kind of come in is you've kind of identified generally what features you want. You want to decide on the parameterization of your model, and this is also iterative, where you're basically balancing precision, recall, basically the ROC um, uh, targets in order to see that your model is not overfitted. So there is some balance between that and basically having high accuracy and precision and recall. You want to really do a lot of out of sample testing in order to figure out is your model actually behaving as you would expect, with basically ideally a low bias and low variance, basically. Um, the last step is productionalizing it. Is now using Kubernetes or Docker, containerizing everything, and then basically deploying it in volume so that it can evaluate and produce predictions for the clients, and of course monitoring and tuning it using challenger models in order to see if there's any drift from the model that triggers you to basically generally launch another retraining exercise. Um, so one common trade-off that is extremely important, especially in the financial space, is the variance bias trade-off. There's a little shiny app in here hosted by our studio to play around with this. It's a little calculator. You can enter you can define your basic data generation process and try different fitting techniques interactively. Um, as you know, variance basically is reflecting the instability of the model to various factors. So what that really means to us is that as I built a sort of a machine learning model, it, how sensitive it is to small changes in the data. Structural models typically have very high bias, right, and low variance, which makes them attractive. Um, Machine learning models don't, right? They have low bias, but they could have very high variance, and you really want to control for that. You don't want a small data set coming in causing a lot of perturbations in your fit. So here we see basically three different examples. One with the orange line being the random forest applied to this sort of data set. You see we're kind of following the trend quite well, but there are obviously spikes when compared to the quadratic regression and nonlinear regression. Really random forest, you see here is low bias, can adapt as the data changes its variance, right? But it has a high variance, but it has a high sensitivity to it compared to the other two. Quadratic regression is definitely low variance, but high bias. It assumes a very specific functional form of the trend. Um, so obviously in this case, it's not really the best fit, but you can kind of see, you can play around with different basically power functions and see how much you can get there. But you can see the difference between the red line and the orange line quite clearly here. Obviously, in this simple ex ante example, very trivial example, the best fit because I generated data, so I know what it should basically kind of look like. We're using basically this nonlinear regression, where in here, in this example, the green line seems to have a decent fit for this data set as a low bias and low variance technique, right? So again, three different techniques, all in the same branch. Really depends on the use case and really keeping track of how much do you want to give up on bias and variance in order to avoid overfitting the technique. Yeah. Again, yeah, basically, really be careful with overfitting and underfitting. You can read the white paper in this URL. You can also look at this app hosted by our studio to play around with this sort of machine learning calculator, create your own data generation process, and create your own fits. Um, so another kind of area where we kind of need to explain it to non-quantitative uh, internal users or stakeholders, right? We've basically kind of created these simple tables to kind of look at every technique and what considerations and what the supervision and complexity is. So generally, like traditional, generalized linear regression models or logistical models, they're typically very tightly coupled to the data and they're sensitive to outliers. So they do need to be recalibrated quite often. So they have a high amount of supervision, but they have low complexity. They're extremely tractable. You can basically know the sensitivities of every factor to your dependent variable, and they're relatively easy to understand. Random forests, can really deal with basically polluted data sets. Um, they're definitely more difficult to explain, and the accuracy can be equivalent to the well-structured. On well-structured and clean data, the accuracies can actually be equivalent to the traditional techniques. The advantage here is there's very low supervision, typically, that they can react to the data set in real time, but they have a high degree of complexity. Then you can look at basically gradient boosting, some complications around the first branch, right? They're definitely low supervision, but high complexity. Now, complexity ties back to interpretability and explainability to some degree, and these have evolved over time, especially on basically the neural network side. And using basically model agnostic explanations, uh, you can really start opening up the black box and kind of explaining to folks what's going on, and also for yourself to understand how their model is drifting or reacting to individual features or independent variables. So has evolved a lot more in the last few years. Um, so now let's go into natural language processing, or in other words, sentiment analysis. We have a This is an attempt to basically to produce a generalized sentiment pipeline. What this really means is we've tried to think through different sentiment analysis problems and what typical techniques can we create as a flow chart, and see um, kind of what the steps would be to actually produce basically a prediction. Um, so we have deterministic models, right? And we have basically non-deterministic models, right? So uh, in general, the first thing is you need to basically be able to parse and extract the text in some machine readable form, right? And then you need to tokenize it. Now, if you're going to go through the neural network side of the equation, right, you're going to need to create annotations and labeling, and that typically involves a human in the loop coming in and reading basically the articles or the sections or the chapters and actually providing a deterministic label against them so that you can use that to train your network. If you go with a bag of words approach, you've got basically a defined dictionary of words of positive, negative, and their weights. And you can either use a prescribed weights or treat them kind of equally in a naive way, or you can use some form of lasso or regularization in order to reduce the dependency of some of those weights against particular targets, so that they can be a bit more curated to the context of the article that you're trying to get to. In the neural network side, you don't have to do that after you've done the labeling. The networks will capture any nonlinearities in the text themselves, assuming you basically parsed it correctly and tokenized it quite accurately depending on the language. In all three cases, you'll end up with a probability score of the polarities, or depending on what you end up with a probability score of the polarities, and you can basically create some categorical variable against them in order to discretize it and basically, show at the end of the day, what your classification is. So, I kind of talked through it a bit, but again, to go back into the simple, hey, how do we explain to business stakeholders what are the techniques and what are the considerations? Plain bag of words. It's a deterministic aggregations. They're dictionaries that need to be designed with that context. Um, Typically, a lot of recalibration will be necessary. Uh, they're they're very dependent on they require quite a bit of supervision, and however, the complexity is extremely low. You can actually easily explain to a user what is going on when you're scoring a particular article with a particular basically polarities. They're typically very deterministic aggregations of the words that are in that article. Regularization is kind of an in-betweener. It does maintain the context better than the plain bag of words, but still requires some form of recalibration, obviously. So there's relatively medium supervision and medium complexity. Neural networks is exactly the opposite of the first, right? It's typically low supervision, but very highly complex. However, what the big value proposition you get is that the context is maintained for your target variable, and it can really capture non-linearities in the text and the assignments that the other two techniques will have very high amount of difficulty uh, to handle. Typically, for difficult languages or for highly context-dependent spaces, we would use neural networks, and you'll see an example later in the case study. But for very say called first party, typically um, Latin or English-based basically languages, you can get away with basically regularized bag of words and bag of words pretty much. So let's go through the first case study. First case study is going to go through sentiment analysis for documents. So to kind of get a little more deeper there, common problem at S&P Global Market Intelligence is that our clients need review large bodies of unstructured data that are domain specific. In this particular example, clients have a significant amount of basically Chinese first party announcements in simplified Chinese. And what they typically do today is they have to manually read them and go through basically these articles quite often in order to extract what was the potential credit risk impact or a potential negative announcement or financial health on that company. So you kind of have to read through a lot of basically pages and sections in order to filter through what they're actually trying to disclose about the company itself. So rather than so the process today is really manual, inefficient, highly dependent on human expertise. So what we wanted to do is automate this process. So at the very high level, we take basically large bodies of scanned images or PDFs. So they're machine unreadable text. We run them through OCR, create basically a structured data set or data frames, and then we run them against a neural network and produce basically the scores that you can see there, along with an ability to highlight paragraphs and areas that had the highest impact to the score, right? The highest relevancy. So because it's a neural network technique, supervised machine learning, at the beginning we really needed to annotate. So we had basically got we work with a third party to basically get reviewers to come in who are native language experts and financial experts. What we did was we OCR the text that we received, and those are like millions of articles, and then we sectioned them out into chapters based on if the document has an outline, based on the outline. And then we built a Shiny app, as you can see in the screen, that allows the annotators to go in, click a particular section, and then highlight the relevant area, and then give it the classification. Sorry, click on a particular section, highlight the relevant paragraph or sentence, and give it a classification. So we did this all in Shiny in our studio, and it was very easy for the users to kind of go in and interact and label. This created quite a rich data set for us to actually train this neural network against. So once we had that, we basically wanted to test it in volume. And at a high level, what we did was we ran it through the chaptering. We run it through another actual relevancy classifier that says, is this generally a relevant article for our financial context or not? If it is, get it through a deeper classifier to actually calculate a polarity against it. And then we basically capture the score at the section level, aggregate it back up to the article, and aggregate it up to back to the company, and we can do this over time to get kind of create a time series. Um, so going under the hood, we've used, as you can see, we actively use both R and Python to build these. So we basically we start with the announcement. We send it before we send it to the OCR engine. We do a lot of document uh, pre-processing using image magic. What we're trying to do is really handle the sharpening, and for documents that are very waterlogged or very fuzzy, try to kind of improve the quality as much as possible before we send it to Tesseract for it to extract, to convert basically the image to machine readable text. Once we have that, then we basically start, we're able, essentially, we get a list of data frames, and we're able to basically start chaptering them out into more into basically a cleaner data set that we can actually work with. Then we basically send that those sections and apply basically sentence and tokenization techniques against it to chapter them out. And then we basically convert the text into a vectorized space model. So we looked at fast text from Facebook. We looked at different techniques. We use about 180 degrees of freedom, and we tested that out to see if we convert basically the text into these sort of matrices or vectors, can we do we still get back the analogous terms that came from here? And we ran iteratively and retrained this until we reached a happy medium where the folks who were reviewing it were confident that the vectorization gives you analogous terms. Once that's done, it's pretty typical. You can basically send the vectors into your neural network, and we've got an input layer, a series of embedded layers, one-dimensional convolutions, and LSTM recurrence, and then finally an output layer. We have a bunch of dropouts throughout in order to kind of control a little bit of the overfitting as well. And then, of course, we package this whole thing into sort of a deployment in our Connect for the users to actually play around with the data set and actually visualize it as a prototype before we productionalize it in Airflow as a batch operation that feeds into our feeds and desktop offerings. So essentially, like one of the things that we basically uh, do early on is once we've kind of evolved through the latter stages, we built basically a typical Shiny app in RStudio Connect. This is an example of the original Shiny app. This is something we can handle. We usually give to stakeholders and client and prospects, friendly prospects, as basically as an advisory panel. And using this app, they can actually interact with the data set, click on particular points or articles or sections that we've scored, and actually start drilling down and playing with it in order to really apply to their use cases. Um, and it's been very helpful for us because we can convert this and eventually into requirements that we build on the desktop. Yeah. Again, this is another example of basically these are companies that had experienced a high amount of distress in China during basically 2019. And you can see from our output, we see that we're actually capturing the negative basically polarity quite accurately. The other interesting thing that you can notice here is that, and this is typical in that country, is that when they announce basically a potential bankruptcy, um, they eventually you get obviously negative announcements, then they eventually restructure, or they might have a government basically buyout or government support, and then they revert back up because they basically received that government support, right? So that's a typical pattern you see in that region. Yeah. So the next case study is on document-based, basically financial statement assignment. This is a product we call ProSpread in S&P. So to kind of give back, to take a little step back, um, you know, we have large non-financial corporates and banks as customers, and they typically lend to smaller and medium-sized businesses. They want to basically maintain sort of a credit outlook on those counterparties. Now, however, these financial statements are proprietary. The small businesses don't announce in the public markets, right? So they will only share it with their counterpart, with who's lending to them. Um, so to do that, we had a secure platform to basically allow the user to upload those proprietary financial statements. Again, these similar to the Chinese situation, these documents are not usually very well organized. They're typically scanned images of printed statements. They're in different formats, and generally the process today is for them to spread using a human in the loop, meaning they will kind of put the document on one screen, on the other screen they have Excel. They type basically the financial line items they want. So we wanted to make that process more reliable and more auditable, um, while also keeping the human in the loop, because quite clearly some of these accounting standards and how they actually verify information um, does need a human in the loop to actually review it before you submit it. So what we did was we built basically ProSpread. Again, to kind of reiterate, you know, this is sort of the problem as it was presented to us is, you've got basically all these waterlogged, weird, noisy documents of financial statements. Our clients are in the middle, and what they really want is just to look at something so organized and uh, and uh, and transparent, similar to basically what we do today with the public companies and the companies we can collect financial statements from. Um, so in order to do that, I mean, again, a similar stack, similar sort of group of techniques, right? We basically run them through the optical character recognition engine. We do a lot of image enhancement. We add table detection in here because we're again concerned about financial statement line items. Typically, those are in tabular format. Once we have basically a structured output of this, we run it through the algorithmic assignment and the user assignment piece. The algorithm assignment basically takes there's two ways. One direct through the semantic matches, like basically word to word, see based on the dictionary, are they close enough? The other is a balancing model, which basically not only looks at the semantic matches, but also we have a chart of accounts, a hierarchy of basically how individual line items should roll up to higher line items. And we look at the numbers as well as that organization in order to imply basically a direct match. All of this can be overridden by the user assignment. User can go in and basically actually reassign particular line items to the way they see it. And when they hit save, it goes back into the user specific dictionary so that the next time the next user will not have to do those same assignments again and again. So there's an online learning component of this that's real time. Um, so under the hood, this is how basically this process looks like. I mean, again, I'm not going to go through every block here, but I mean, generally, pre-processing, you get images, you got to do a lot of sharpening, artifact removal, table detection. These are pre-trained neural networks. Then you go through basically tidying the tables and finding out which ones are actually containing relevant financial line items in the balance sheet, cash flow, income statement hierarchy. Then you kind of go in and then start applying some form of semantic matches and balancing. And then once this is done and the user has actually agreed to it, it gets submitted into the database and it can be scored using our credit models. And then basically two ways to visualize it. Obviously, as a prototype, we basically did JSON and Shiny through our Studio Connect, as well as Excel-based templates for the clients to kind of assess this as well. Now it's part of the desktop offering. You can go onto CapIQ and actually take a look at actually try this data set yourself, try this app yourself. Again, because this is sort of dealing with large documents and there's a definitely an architecture behind it, and we basically use this type of architecture with S3 and basically EKS endpoints in order to S3 to save basically documents in a secure space, and EKS to basically call different types of endpoints using Kubernetes and Docker there, right? And this all is saying the high-level orchestration. We have actually queuing. A lot of the clients we have are typically dealing with smaller size documents, so we didn't want the clients we were dealing with typically large documents to basically overlap with the small ones. So we have two basically clusters and a centralized queuing and routing for load balancing, and we do basically elastic scaling horizontally in order to manage basically that series of requests and keep everybody with a reasonable SLA. Um, this is an example of the Shiny app. This is very, very early on. Now it doesn't look like this at all, but basically this gives you an idea. Like in Shiny, you can you can actually build very simplified UIs that clients can use using these neural network using these machine learning techniques. So here you've obviously got the document. Here you've basically typically this is what your algorithmic assignment is. You've got cues in here for the user to actually pay attention to. And if they need to sort of do an Excel-like edit or correct something that was mis-OCR'd, they can actually do it in the top left pane here. Yeah. Um, so in conclusion, try it. These two apps are actually available live. Here are the URLs to them. Both China Sentiment Analytics are available on S&P Global Marketplace. There's a thought leadership piece around it that's available in the second link here. ProSpread, the proprietary financial statement spreading, is also available at this URL. There's more information there, and you can you can actually try it out as a client. Future extensions. Really looking at more transformers, basically. So BERT and Elmo. There's been a lot other types of transformers that have happened since we've added this, and to kind of improve the neural networks context sensitivity, right? Obviously, performance and tuning. NVIDIA's done a lot of work around basically managing large data sets on GPUs using Rapids. And this is something we're actually looking to use as well. And really expansions on transfer learning, where I've trained something on one type of data set. Can I actually use that network and apply it to something that's quite similar as much as possible, right? The other thing is that when we touched upon this is really model agnostic explanations. Any way to kind of create transparency around your machine learning supervised machine learning application is very, very important. This paper is really, really great. You should probably read it if you haven't already. We've used Lime quite a bit. It's simple, it's easy to explain. It is computationally expensive, but it really kind of gets us to the last mile of basically opening up the black box. And in conclusion, we continue to basically work with unstructured data and provide basically relevant, reliable machine learning pipelines to our customer base. This is my collaborators, Mikhail, Saeed, Bin, and Viraj. And that pretty much concludes, and we can open it up to Q&A. Thank you very much.